second thing was computing the values of cosine and sine functions. Well, we conveniently use calculator and hit the button. Well, put into a situation, you suppose you are in the company who are making this calculator or thinking about doing things like that, or you put yourself in a situation where 100 years and 200 years back that you don't have a calculator, and we want to create a very, very accurate approximation of the values of this thing. How are you going to do that, right? They have all this built inside the calculator, and how do they actually got those numbers? And this addition formula will give us a clear idea about how to approach that problem. All right. So for that, this is a motivation. Here's our circle. Unit circle is x-coordinate, and y-coordinate are the cosine value itself and sine value itself, right? We know some of the values. Suppose you have a calculator, or you have very smart, a school of very educated slaves. So you give them number, they calculate it. They just can't do cosine and sine. They'll do square root, whatever. You give them, they'll calculate it, right? Slaves of computers, though, who actually compute things. All right, so you started like that. All right, what do we know? We know cosine zero value. Do you know cosine zero value? So you're not supposed to hit, here's a degree. We're going back to geometry problem. I don't want you to hit the calculator. You're in a situation, you don't have a calculator. You can only use a calculator for square root and arithmetic and algebraic calculation, not transcendental calculation like cosine. What is cosine zero? 0 degrees here. What is cosine? X-coordinate, right? What is x-coordinate? It's 0 degree. 1, because this is the 0 degree. X-coordinate there is 1. How about here? What is the angle there? 90 degree. And what is the cosine 90 degree? X-coordinate, right? 0. That's right. So going from 0 to 90 degree, cosine value varies from 1 to 0, right? Decrease. Right in the middle, what would you say? Cosine of what? Angle. 45 degree. Who? Remember 45? That was a special angle. In your mind, right above your phone, here is this triangle 1, 1, root 2, right? That shows up. That is, what is the value here? Cosine of 45? 1 over root 2. So you give this to your slaves, calculate it, and they're gonna calculate this 1 over root 2, right? 1 over root 2 is relatively easier to calculate. And there are mechanism, there's algorithm, you can approximate easily and things like that. Alright? Is that okay? So next idea is if we're going to divide this one too, that will be between 0 and 45, it will be 22.5. If you divide 45 into half. Okay? And then here's a 90 degree and 45 degree, and divide it again. So that's a bisecting. So whatever that is, I'm going to talk about it. So you calculate all these values. I'm going to show you the method. If you know these two values, you can relatively easily calculate the cosine values right in the middle. And cosine value right in the middle. It's not half. Angle's a half, but cosine value is not. Once you have this 1, 2, 3, 4, 5 values, you begin to split again, 1 and split again, because we know once you have these two angles, we can calculate cosine value right in the middle easily. When you do that again, maybe a couple more times, and realize that, wow, this is already very, very fine and a lot of information. So if I have 65 degree, and then you can go to where is a 65 degree fit in, and using those two values adjacent to that, and you have a clear idea about how this cosine 65 degree is, for example, approximately what. Is this idea okay? Yeah. So if I have two angles for which I know how to calculate, how am I going to calculate it right in the middle? That is the method in here. This bisecting problem is algebraically, and we can easily construct these things without you actually measuring any magnitude. This is called construction problem. Bisecting is known, is easy, but trisecting turns out to be impossible. Many people tried. There's a lot of anecdote about those people who try to prove smart, and throughout history, I'm going to trisect an angle without using any magnitude. Just measuring here and measuring there, and straight line and circle. Boom, I happen to trisect and give an arbitrary angle. It's called construction. It's not possible, and algebraically is also impossible. The difficulty is compared like this. You know, the quadratic formula usually is less than one line in our usual legal size paper, right? Stating the quadratic formula. Stating the cubic formula takes almost entire page of that piece. So the difficulty going from bisecting and trisecting is well represented by the algebraic difficulty of doing things like that. But bisecting is not difficult, so I'm about to show you that. So it uses a power lowering formula. So here's our first exercise today. State the power lowering formula. Power lowering formula. This is it, right? This is power lowering formula. If you have sine x squared, the whole quantity squared, you can write as a pure sum like the sum of pure waves, 1/2 and then another pure thing. All right, but if you look at the relationship between the angle, here is the angle x radian, for example. Inside here is 2 times the x in there. Here is x radian, is 2 times x. For example, if I have 22.5 degree in here, then what is 2 times it? Remember the 22.5? 45. So right hand side is, I know 45, right? So right hand side I can compute. The left hand side means sine of 22.5. That seems like a nice formula. So that is the formula we're going to use. So here is called half angle formula. I'm going to introduce two versions. But both versions are very useful, and you can see that immediately. You know, you can easily obtain one from another. So what I just said is that, well, here I want you to notice the sine squared x is really sine x, the entire quantity squared. Remember that? That's an abbreviation of this thing, sine x, the entire thing squared. So we want to isolate sine x. So here's the sine x. What do you think the sine x here is? Square root, right? Yeah. Right hand side of the square root, 1/2 minus 1/2 cosine 2x. There. But do you know why there's a space there like that? Plus minus, right? Whenever you put square root, you've got to consider the plus minus. We don't know anything about x in here. If x is in third quadrant, then you know sine value must be negative. Remember that part? So that could be negative. If x here is second quadrant, then it's going to be positive. We don't know anything about it, so it must be stated like this, plus minus. Does that make sense? So here is number 2. Sine, no, it's a cosine, right? Cosine x is plus minus, what do you think? 1/2 plus 1/2 cosine 2x, right? You look at the second formula of a power lowering formula, if you put it there, and you have this thing. There's no half angle, but relationship is like this, and this angle here is half of that angle. Okay? So it's a different version, often. I'm going to plug in theta over 2 in place of that x there. Okay, so x is theta over 2. That's exactly the same formula. It's arranged slightly different. Here's plus minus root 1/2 minus 1/2 cosine. So if you multiply 2 to x, what happened? X is theta over 2. 2 times x, if x is theta over 2. 2 cancels, right? I hope you see that's just theta. Alright? Here's 2 times x is theta. That's what I'm using. Okay. Second version is also stated like cosine theta over 2 is plus minus 1/2 plus 1/2 cosine theta. If you compare these two versions, they're exactly the same. You just change the variable in a slightly different shape. But both are useful. And you see by staring at this formula, which I call and they call half-angle formula, do you know where it came from? The shape of this one, 1/2 cosine 2x, 1/2 plus 1/2. What was that called before? It was power-lowering formula, right? Just remember that half-angle formula is immediately kind of derived from power-lowering formula. Then I think it's easy to remember this one. Is that right? All right. So why don't we just get used to this? So I'm going to pull it up there. Hide it. I also want you to hide it in your note with your phone, whatever, hide it and try to write this one down one more time. It helps you to follow the content when you're on top of this technical result. It's a simple formula. So state the half-angle formula. You don't have to write down everything, just any part that you remember, half-angle formula. Right, these are the half-angle formula, and we're going to apply to get some of the values on this circle that I marked like this, right? Okay, so let's start with this exercise. Compute cosine. Remember, this formula really involves everywhere cosine, cosine. So if you stick to the cosine, all you need is a cosine, and it turns out it's better. Once you know the cosine, sine is calculated through this equation. X is a cosine. If you know cosine value, sine value is just 1 minus that square value. All right, so compute cosine 22.5 degree. So I want you to look at the formula. And you're allowed to use a calculator, but not cosine 22.5, right? Suppose you don't have that key. You can only calculate square root and then things like that, right? Right, was that okay? If you use the second formula, that 22.5 become 45, and you recognize that we know 45, right? What is cosine 45? 1 over the square root of 2. How about this circle? Why did I choose positive here? What's that? Because it's not negative number, is that what you said? Why is it not negative? Because it's positive? That's circular reasoning, right? It's because of 22.5. Which quadrant is it? First quadrant. You know cosine in the first quadrant is a positive. We state it like this because we don't know what this theta is, right? Does that make sense? So if you remain in the first quadrant, then it's going to be always a positive. But we eventually look at other angles as well. But right now, it's going to be always a positive. All right, so here it is, 1/2 times 1/2 times, what is it? 1 over root 2. It's really nasty thing to put into a calculator, but let's just pretend Let's just do it actually. If I want to pull out your calculator and compute this number. Square root is a lot easier number to calculate. So pull out your slave and ask them to compute the square root of this thing. And I want to have, let me have the 4 decimal places. If you really hit cosine 22.5 degree now in the calculator, hope you find its numbers almost the same. Okay. All right. That was the first step for that angle right here. That is a 45. That's 22.5, right? Now we're going for this angle, and eventually think about keep doing this one. We just happen to two angles, and we better have a more convenient formula for that. So here's another formula just for today's class, right? I have angle theta 1 and theta 2, right? And we want to know the angle right in the middle. Can you algebraically formulate the angle right in between? What's the formula? It's like a midpoint. If I give you 30, I made 30 points, and next test I got 50 points. What is right in the middle? That's the average, right? Yeah. So how do you calculate the average there? Right. The sum of these two things divided by 2. Is that right? 2 squared divided by 2, that's the right in the middle. That's the midpoint formula. All right. We want to calculate the cosine of that guy, right? If we happen to, by doing that, I have 90, and here's 0 and 45. Now I know 22.5. So we know all this value, and we're going into another bisecting angle in here. So what is this cosine of that guy, right? We know cosine theta 1 and we know cosine theta 2. Can we write this one in terms of that? That's the goal. So what comes to your mind? If I write it like this, maybe that's going to give you a clear idea on what I'm going to do next. You split it like this, and what formula are we going to use? To break this addition in here? Addition formula, right? So it's a cosine theta 1 over 2. What is it then? Cosine theta 2 over 2. Is that right? And minus sine theta 1 over 2. Sine theta 2 over 2. So that's the addition formula. We didn't reach the theta 1 yet. It's still theta 1 divided by 2, theta 2 divided by 2. So what is the next step? How do you get rid of this theta 1 divided by 2? Today's formula. What was that? Half angle formula? Right? That's the half angle formula. So let's use that. What is half angle formula for cosine part? There's a square root, right? We're doing this one for acute angles, so they're all positive, so let's not worry about plus minus. What was the cosine half angle? 1/2 plus 1/2 cosine theta 1. Is that right? Cosine theta 2 is similar, just 1/2, 1/2, just a subscript change. That is now, if you look at this one, 1/2, 1/2, we know this value. We have calculated previously, theta 1, theta 2, so we can just stick it in there and calculate again. So it's negative. Sine formula goes like this, negative 1/2, negative cosine theta 1, negative 1/2 cosine theta 2. Here it is. This is a formula. If you have cosine theta 1 value and cosine theta 2 value, what is the value right in between there? That is this formulation right here. and we were able to use addition formula and half angle formula to bring it out like this. And we know this values right here, right there, right there, and right there. All you have to plug in and calculate the square root. Typing this one into calculator is very likely that you're going to make a mistake. So so I'm just going to do one example and skip actually calculating in here. So what was the next target? It was this 90 degree and 45 degree, right? 90 degree and 45 degree. What is in between 90 degree and 45 degree? I think it's 67.5. So we're back here. We have 45 degree. We looked at it earlier, and a 90 degree right in the middle. Here's a 67.5 degree. If you calculate this one, 45 plus 90 divided by 2 is a 60.5 degree. So we're saying, what is this cosine of 67.5 degree? That is, the theta 1 is 45 and theta 2 is 90 degree, right? So you apply the formula here. 1/2 cosine of theta 1 is a 45 degree. 1/2 plus 1/2 cosine of 90 degree. Remember the value of 90 degree, cosine 90 degree? Nope. It's cosine 45 degree. It's minus there. Cosine 90 degree north pole, x-coordinate north pole, 0, right? Yes, go ahead. All right. The order of this one doesn't matter. So cosine 90 degree was a 0. Remember, that was the x-coordinate at the north pole, 0. And this one is we have it already, 1 over root 2. So you calculate all that. And it's complicated radical form, but all they wanted is the approximate value. So I have it here somewhere, I think, is a 0.3826. So they calculated and got this value. Now we have 0 degree, 22.5 degree. So let me write that down. 0 degree, 22.5 degree, and we have 45 degree calculated, 67.5 degree I just calculated here, and there's 90 degree. Right? So we have this decimal expansion of this one. All right, then they do it again. All right, what is the angle in between in here? And I did all the calculation. Is 11.25 in between in here, 33.75 degree, and in between here, and the 56.25 degree. In between there is a 78.75 degree. So because we know all these values, right? We have recorded it, and you go here and plug it in here again to get these cosine values. And do it again and again, right? And we have very accurate value of a table of all these values. So if you have something else, figure out which interval it belongs to, and then by looking at those two values, and you have a clear idea what that cosine value, first few coordinates should be, and things like that. Right? If you divide it more and more, it's more and more accurate values. I'm sure the ancient time when they prepared these tables, it is constructed in this way. Once you have that accurate tables, it's very useful for construction and architectural purposes. And if you measure some celestial motion, things like that, the accurate the value further down to 100 digits, and they're very important. All right? That was the second application I was talking about. right? This identity thing that introduced and this free analysis is very, very useful for calculus 1 variable calculus and calculus 2, the integral calculus, and you use this identity a lot to speed up the calculation, more efficient calculation and things like that. But when you enter calculus 3, which is multivariable calculus, not only you use all this thing, but you use all the geometry that we learned beforehand of this analytic geometry, law of cosine, and all full force of everything you learn come back and come into play in 2 variable and in calculus 3. So everything we learn here is very, very important for later to further study the direction of any higher mathematics, right? Right, we're going to do one more problem and that'll be it today. Any question about what I just did? No? Does that make sense? Application? Why on earth are we doing this? And that's, as I think it's a neat idea. You know, it's already known, so why should I learn this thing that is all done deal? Well, it's the idea. If you think about the idea, you have one step at a time. It eventually gets you there. You can program all this. So not by doing hand in the computer, you can generate just using this algebraic procedure. You can actually build up entire table of a cosine value using the computer program, things like that. So that's idea is what I value, algorithm. Okay, so I hope you saw that idea introduced right now. This one is web of science stuff. All right. So they gave you this sine x value and ask you to calculate the other values. So why don't I do number 37? Sine x, I'm going to change it a little bit, is 3/5. And x is not in the 0 in the 90 degree, but it is in 90 degree and 180 degree. So that this makes sense. The sine x value is a positive, right? So the only positive candidates there is first quadrant and second quadrant. Now it's in the second quadrant, but the problem said it's first quadrant. I changed it. And then it says compute sine of x over 2, cosine of x over 2, and tangent of x over 2. That's what it's asked to compute. Let's compute. So what kind of formula comes to your mind? Some obvious formula, right? Half angle formula. So here, let me start this one for you. All right, what we want is x over 2. Remember, general formula, half angle formula has a plus minus thing. Remember that? Plus minus square root 2. So this inequality will help us to determine which sign we need to have. So if x is in between 90 degree and 180 degree, what do you think is this limit is? 90 degree was there. You divide both of the side of the inequality by 2. So it's 180 degree divided by 2. Right? Fair enough? Then what is the left-hand side? 45 degree. X over 2. Right-hand side is 90 degree. Right? X was in the second quadrant, right? What about x over 2? Where is this? Yeah, where is x over 2? 40 in between 45 and 90, so it's the first quadrant, right? Yeah. This one is the second quadrant. Now x over 2 is in the first quadrant. So sine of x2, we know it's a positive. Cosine of x2 is a positive, and tangent of x2 must be positive. Okay? Now I'll leave the rest of the part exercise. Exercise here. Finish it. Compute cosine x over 2, sine x over 2 and that, using half angle formula. In the half angle formula, there is a positive, negative, square root 2 is always a positive because of this one in here, right? We choose positive let me just explain it here. Y equals 3. 5, 3 is shorter, so that's over here. That's x radian. That's x comma 3. Does that make sense? That's the situation. That's not x there. X is not good. What is it? Capital X? Because x we're using as a radian here. All right. So the cosine x value is negative 4 over 5, right? That's the x coordinate negative 4. So we got that cosine x, and go back to this question mark. This is what we wanted. I'm putting the stars around it. This is what we wanted. And I know the cosine x value. And once you're done with that sine x over 2, finish, go and compute cosine x over 2 and tangent x over 2. Okay? It's your exercise. Yes? How about tangent? What are you going to do? I didn't give you any formula about tangent of half angle, but you know tangent is in terms of sine and cosine, right? Remember that was a sine of x divided by 2 divided by cosine of x divided by 2. Sine divided by cosine. That's tangent. So what's sine? 3 divided by root 10. Is that right? Cosine is 1 divided by root 10. And root 10 cancels, becomes 3. So tangent x over 2 is 3. Well, that's it. This is the only web assigned problem you're going to have today.